Okay. Hey, good morning, everyone. Welcome to day 3, track 2 of DVCon. The focus of this track is on design verification, reuse, and automation. My name is Ashish Mathur, and I'm part of system modeling team at NXP. I will be moderating this track today. We have got 4 great papers in this session. 2 are focused on SoC functional verification and integration aspects, and we've got the rest of the 2 are focusing on performance verification and validation. The first paper in the session is titled Methodology Avenue, Power Clock Reset Verification for a Complex SoC. Authors are Ashik Ghona, Raghavendra P, and Raghavendra Jain from Intel. So we have allotted 20 minutes for video presentation by the authors, followed by 5 minutes of Q&A. Please use the Q&A tab on your screen to post questions as we go through the presentation, and I will pull those questions at the end of the presentation to post to the authors. Also, there's a poll option that comes with the Q&A tab. Please provide your ratings for the paper at the end of the presentation. Okay, so without much ado, I will hand over to Ashik. Please go ahead.
Ashik Ghona, and I'm going to present paper Methodology Avenue, Power Clock Reset Verification for Complex SoC. I have co-author Raghavendra P and Raghavendra Jain for this paper. So today's ML and Vision IP based SoC have numerous IPs integrated into it, and it has a complex power up, power down sequence, and clock and resets are traversing from source to destination under various different modes, right? So we might see multiple issues while doing the SoC bring up on board, and to catch such issues in early stage of verification or project, it's very useful for overall project. So in this paper, we'll discuss such issues, and we are proposing a methodology which will catch these kind of issues in very early stage, like in functional DV stage, right? So we'll discuss about issues which we are going to address. So first is clock and reset signal traversing through power domains under different modes. So in SoC, we have functional mode, test mode, and debug mode. And clock and reset signals behave differently in such mode. Next one is indeterministic value for clock reset fan out. So we might be seeing unknown value on clock and reset fan outs. In some simulation, we might be seeing X. Cross connections. So it's possible that clock and reset signals are connected wrongly from source to destination. It might be connected to different IPs rather than expected under different SoC modes. So we might be seeing glitches, especially in DVFS scenarios and power gating scenarios, while enabling or disabling clocks. For power up and power down sequence, it's possible that power related signals, isolation, retention, or power switch control should toggle in correct order. We might be seeing issues with respect to JTAG chain. So different field of JTAG chain should behave properly and do the correct functionality. So as a solution, we are proposing a Perl parser based methodology, which is passing 2 different spec, power clock reset plan spec and clock reset integration connection spec. So we will see the proposed format for this spec, and Perl parser will generate collaterals which we can use in functional DV for 3 different category. So first collateral is configuration stimulus, the second one is checkers and assertion, third one is functional coverage. So this is the parser, this is the format which parser is using. It has information related to PLL sources, various frequency under various frequency mode like mean or max or boot frequency mode. It has information related to clock divider, and this is the frequency value, and this is a PLL value from which clock divider is using as a source. Then we have information related to clock gates. In this spec, we have information related to clock and reset connectivity from source to destination. The first column is showing clock and reset signal at the destination. Second one is showing at the source. And for clock, we have information related to mean or max frequency for each and every clock node and respective clock gate control registers. For reset, similarly, we have soft reset control registers. This is a flow chart which is showing that Pearl parser is taking input uh, as these two spec, and it generates collaterals like stimulus, checkers, and functional coverage. So under stimulus, it generates the power up down SV sequences for each and every gated power domain. Then it also generates the PLL, clock divider, clock gate, and soft reset related configurations. Basically, it generates sequence as well as constraints for this programming. So for SoC level verification, we need C APIs for all of this configuration. So for that, it generates C APIs for similar PLL programming, clock gates, reset, clock dividers. For JTAG also, it generates a constraint and programming sequence for JTAG chain. Under checker, we are generating assertions to detect the clock and reset fan outs toggle. For to catch the glitches, we have glitch detector binding for each and every clock and reset fan outs. For clock fan outs, we are checking various conditions under functional mode and different modes using clock assertion, using the clock assertion related properties. For to validate the clock frequency for across the various frequency plan like mean, max, intermediate, or boot frequency plan, we have frequency checkers which we are binding on all the clock fan outs. Under functional coverage collateral, we are generating cover groups, cover points, and cross coverage for PLL configurations, clock divider, reset. So for configuration and stimulus, we are generating SV constraints for the clock plan like boot, mean, intermediate, and max. We are also generating SV sequences for power up and power down, as well as sequences for programming clock divider, clock gate, and PLL programming. We have sequences and constraints for JTAG programming as well, and a C API for SoC level verification. So in subsequent slide, we'll see how each of these generated collaterals looks like. So left side is the showing the C APIs. So this is the first C API, which is power domain init is API call, and previous snippet is showing the API definition. Similarly, we have API call and API definition for PLL programming, clock divider programming, and clock gate programming. Right side one snippet code is showing the SV sequences for power domain. Similarly, we have snippet for clock divider programming. So these are constraints. Through constraints, we are controlling the programming. We have sequences for PLL locking. Then we have we are able to generate the sequences for reset control and clock gates control. So this is the sequence call, and in sequence we can pass various constraints which we have defined, and by providing this we can program the clock gates or PLL under the hood. Under checker and assertion collateral, we are binding frequency checkers for all the fan outs. So we have binded glitch detectors for all the clock and reset fan out, and using clock assertion binding, we are checking various properties of clock and reset fan outs. For low power mode, we might not be able, I mean, we might expect that some signals should not toggle. So to check those interesting signals, we have assertion binding for the same. So this slide is showing how clock fan out is given to the virtual interface, which is used by clock frequency checker class. Similarly, we have glitch detector macro, which is detecting glitches on all the interesting clock and reset fan outs. So clock assertion macros are detecting various clock and reset properties. So basically, using this methodology, we can bind such assertions using those XLS format and parsing them. So for functional coverage, we are able to generate the cover bins and cover points for PLLs, clock dividers, and clock gates. We are also generating cross cover points for various frequency plan for DFS scenario. And for JTAG also, we are generating functional coverage, which is very helpful in debug mode and to validate the JTAG chain functionality. So this slide is showing the result. By using this automation, we are gaining a significant amount of effort, which would have been spent if this methodology is not existing. So this blue bar is showing the traditional approach, and yellow bar is showing how much time or effort we could reduce using this methodology. So for stimulus collateral front, we don't need to write constraints and sequences manually. Automation is generating this for us. For a checker front, we don't need to bind assertions and frequency checkers manually for all the clock and reset fan out. Functional coverage front, we don't need to write the configurations for this PLL, clock divider and clock gate and soft reset related configurations. By using this methodology, we could reduce the debug effort and time significantly. So we have deployed this same methodology in another project, so which is showing its horizontal reuse. And so we deployed this methodology at IP level first, and then we could reuse the same constraints and checkers at SoC level, which is showing the vertical reuse. Summary. So this methodology shows that by using this kind of automation, we can do so many tasks automated, and which will help us to save manual effort and time. By using this automation, we found numerous bugs at very early stage of our verification in SoC project. It helped us to generate the DVFS scenario very quickly and seamlessly, as user never had to look at the lower level configuration due to this automation. So during the project, a lot of changes were happening from architecture side and design side. So it helped us to consume those changes in our TB. We never had any need to remove any configurations or registers definition manually. By using this automation, all the sequence APIs, everything was getting updated automatically. So ultimately, it helped us to save the significant amount of debug time, because it prevented human errors which can happen due to manual coding of these configurations and checker binding. And yes, it helped us to enable the horizontal and vertical reuse. Thank you.
Good results. So I think we are just about time. Have a minute or so for a question or two here. If there guys any questions from the audience, please post them in the Q&A tab, and we'll get the answers from the authors. But while we wait for that, so I have a question that you mentioned that this methodology has been applied first at IP level and then subsystem and SoC level. So just wanted to understand that, was there any changes needed to adapt it across these abstractions, or it's pretty much scalable across different hierarchies?
Okay, so there were no changes at all, because for configuration sequence for PLL programming, clock divider, clock gate, all were reusable at uncore level. And as we see, this methodology is also using C APIs. So C APIs we are using at SoC level directly with code version of the SoC, right? So there were no changes at all. All these sequences were completely reusable.
Okay, perfect. Thanks for that, Ashik. Okay. Yeah, I think you would have maybe a couple of more questions, but I think we're running out of time. So again, a big thanks to all the authors. Great work, guys.